Hello everyone, how are you all? This is your ma'am Akshita and I'd like to welcome you all to the session today. So previously we spoke about, or I would rather say we did the part 1 of coordination chemistry, where we learned about, the various terminologies to understand coordination chemistry, to understand coordination compounds. After that, we learned about the Werner's theory, we learned about, the nomenclature, and finally the isomerism. In our session today, we shall be learning about the bonding in these compounds. How is it? What kind of hybridization it has? So all of that shall be learnt in our session today. So what are we going to do in our session today? As you know, and as I've already stated, in our session today, we shall be talking about VBT, that is nothing but the valence bond theory. The valence bond theory. And we shall also be talking about CFT, which is nothing but crystal field theory. Alright kids, so in our session today, we shall be learning about the valence bond theory, that is VBT, and CFT, that is nothing but the crystal field theory. Now, in Werner's theory, we learnt about the primary valency, we learnt about the secondary valency, but there were a lot of questions that were unanswered by it. The questions like, why only certain elements form coordination compounds? Why is it so? And why there is directional property of bonds? Why is there a directional property of bonds that is observed, that is seen? Not just that, why there is magnetic and optical properties of the coordination compounds. Now this is something that is there, but Werner's theory was unable to explain it. Then came the need to understand the bonding in coordination compounds, because based on the type of bonding that is present, we can understand or we can answer these questions one by one. So under this, multiple theories were there. The valence bond theory was there, crystal field theory was there, okay, ligand field theory was there, molecular orbital theory was there, and all of these came one after the other. They were explained one after the other. However, what we need to learn on what our academics, or I would say our sphere, to understand this particular topic only deals with the valence bond theory and the crystal field theory. It deals with the valence bond theory and crystal field theory, and we shall learn it now, starting with the valence bond theory. Now, what does this particular theory state? That according to this theory, the metal atom or ion can use N-1d, Ns, Np or Nd orbitals for hybridization. You know that pure orbitals combine, right? Pure orbitals combine and they form hybrid orbitals. Now, when these hybrid orbitals are there, it is these hybrid orbitals that participate in bonding. Now, in this particular case, the pure orbitals that are responsible for hybridization are N-1d, okay, Ns, Np, Nd orbitals for hybridization under the influence of ligands. This happens under the influence of ligands. It just does not happen just for the sake of it. No, it happens under the influence of the ligands to yield a set of equivalent orbitals of definite geometry. Now, these equivalent orbitals that they're talking about is nothing but the hybrid orbitals having equivalent energy. You have already learnt in chemical bonding that the number of pure orbitals combining is equal to the number of hybrid orbitals formed, and the energy of the hybrid orbitals formed are equivalent. They're equal. All right. Such as, now what are the different orbitals that are seen? What are the different hybridizations that are seen or geometries that are seen? One is square planar, the other is tetrahedral and octahedral. And there are multiple, but we deal with coordination number 4 and coordination number 6. And coordination number 4 is capable of forming square planar or tetrahedral, right? And coordination number 6, you see the geometry of octahedral. In coordination number 6, see the geometry of octahedral. Now, these hybrid orbitals and ligand orbitals are allowed to overlap with each other. They are allowed to overlap with each other, which the hybrid orbitals of the metal, okay, and ligand orbitals, okay, they are allowed to overlap such that the ligand which is there, you know that in coordination compound there is a metal and there is a ligand. It is the ligand that is donating electrons to the metal. It is the ligand that is donating it is the ligand that is donating the electrons to the metal. It is the ligand that is donating the electrons to the metal. Thereby, the ligand acts as a Lewis base. It acts as a Lewis base. And the metal, on the other hand, acts as a Lewis acid. It acts as a Lewis acid. Alright, so the hybrid orbital of the metal combines with the ligand orbital, okay, I'll not say combine, I'm sorry, it overlaps with the, hybrid orbital of the metal and in such a way that the ligand donates its electron pairs to the metal, okay. Now, under this, now what happens is there are two types of complexes that are formed. There are two types of complexes that are formed. One is the inner orbital complex and the other is the outer orbital complex. One is the inner orbital complex and the other is the outer orbital complex. Now, what is the difference between the inner orbital complex and the outer orbital complex? The difference between the inner orbital complex and the outer orbital complex, I'd like to explain it. Yeah, I'd like to explain it over here. Now, there are two types of complexes that are formed, beta. One is inner orbital complex and the other is outer orbital complex. Now, the term itself, these terms itself, this particular phrase itself is explaining the inner orbital complex. That means the inner orbital is involved, okay, in hybridization. That is the formation of the hybrid orbitals. Whereas in outer orbital complex, the outer orbitals, I'll say, are involved in hybridization. How, ma'am? How, ma'am? That should be a question. How, ma'am? So, very simple. The n-1d orbital along with ns and np are responsible. Here, the n-1d, n-1d, okay, along with ns and np orbitals are involved for hybridization. Whereas over here it is the ns orbital, the np orbital and the nd orbitals that are involved in hybridization. All right. So you see that n-1d orbital is involved in hybridization. Okay, and here the nd orbital is involved. That is why they are known as, since the inner d orbital is used, these are known as the inner orbital complexes and they are known as the outer orbital complex. Now, why does this happen? This happens in the presence of strong field ligand. Now, what is a strong field ligand? We will learn about it. This happens in the presence of weak field ligand, generally, okay. Another thing that you need to know is inner orbital complexes generally have low spin. They are low spin complexes. You'll understand why. They are low spin complexes, whereas outer orbital complexes are high spin complexes, generally. Okay, okay. Alright, so this is basically the demarcation between the inner orbital complex and the outer orbital complex. And one thing that you need to understand is, in the case of coordination number 4, in the name of coordination number 4, there are two hybridizations that are possible, that is dsp2. As you see, this d is coming before s, that means this is the inner orbital, this is the inner orbital, inner d orbital, and the other one is sp3. sp3. In totality, there are 4 hybrid orbitals over here. There are 4 hybrid orbitals over here as well. And this dsp2 is an inner orbital complex. Inner orbital. This forms inner orbital complexes. Whereas sp3 forms outer orbital complex. It forms outer orbital complex. Similarly, for coordination number 6, there are 2 hybridizations. One is D2 sp3, the other is sp3 D2. Okay, you can see D2 sp3 and sp3 D2. Here the D is before S, that means the inner d orbital is being utilized, and thereby this forms inner orbital complex, whereas this particular one forms outer orbital complex. Alright, bacha? Alright. Now when you talk about the geometry, fine, this is the hybridization. What is the geometry though? So the geometry, when dsp2 is there, when dsp2 is the hybridization, the geometry is square planar. It is square planar. Whereas when sp3 hybridization is there, the geometry is tetrahedral. You have already learnt about the coordination polyhedra in the previous lecture. Therein you have seen the shapes of square planar and tetrahedral. Whereas for coordination number 6, be it D2sp3 or sp3d2, the hybridization may vary, but the geometry is octahedral only. The geometry is octahedral only. This is what you need to keep in mind when you're talking about VBT. This is what you need to understand. This is what you need to keep in mind when you talk about VBT, when you talk about valence bond theory. Alright. So with this, you have understood what inner orbital complex is, and you have now understood what outer orbital complex is. One question of course that you have in your head is, now what is the strong field ligand and weak field ligand? So let me tell you, for now what you need to keep in mind is, for strong field ligand, what you need to keep in mind is, you can keep CO and Cn minus. These are strong field ligands, whereas weak field ligands include the others like NH3, H2O, EDTA, etc. And you'll see why. Alright, so you can remember this for now so that you can understand VBT. Now let's try to see how this bonding is actually taking place. And let's start with coordination number 4. So depending on the nature of orbitals involved, hybridization geometry of complexes are tetrahedral and square planar, as you have already seen, and you're already aware of the fact that when it comes to tetrahedral, this is because of the formation of outer orbital complex, or I would rather say they are the ones which form outer orbital complex, whereas when you talk about square planar geometry, this is because, or they form, inner orbital complex. So let's now try to understand the tetrahedral complex having the hybridization sp3, Now how is this going to be there? For that we need to take the example of NiCl4 2 minus. So what is the electronic configuration of nickel? It is 3d8 4s2. So Ni plus 2 will be 3d8 4s0. As you can see over here, there is mistake. It is 3d8 4s0. This is the electronic configuration of nickel beta. This is the electronic configuration of Ni+2. Now the question is, how is the chloride atom going to donate its electrons, and how is the hybrid orbital formed? So here the valency shell electronic configuration is going to participate, and how? So this is Ni+2, this is the Ni+2, and this is the electronic configuration, that is 3d8 4s0. Now what is going to happen is, there's 3d8, there is 4s, now there's 4p. We already know that CO and Cn minus, these are strong field ligands, but here chloride atom is there. Chloride on the other hand is not a strong field ligand. So what is going to happen is, strong field ligands, they allow in pairing beta, they allow in pairing. Here pairing does not take place because it's not a strong field ligand. Now this S and P thereby they combine to give rise to sp3 hybrid orbital, and in this hybrid orbital the 4 chloride atoms donate their electrons, thereby giving rise to tetrahedral geometry having sp3 hybridization. I hope this is clear. Now let's try to understand square planar. Square planar complexes. Square planar complexes having dsp2 hybridization. Again, we have taken the example of Ni. Here again, the oxidation state of Ni is Ni+2. So that is again going to be 3d8 4s0. It is going to be 3d8 4s0. All right. But here what is important is Cn minus is there. Cn we know is a strong field ligand. So now see what is going to happen. Now this electron that is there over here, it is going to get donated. And upon getting donated, this electron comes over here. One thing that you need to understand is, this electron comes over here, and now when this happens, when this particular electron comes over here, this empty d orbital that is there, it participates along with one s orbital and two p orbitals to give rise to dsp2 hybridized orbital. And in this hybridized orbital, the cyanide, okay, Cn minus donates its electron pairs, thereby giving rise to dsp2 hybridized orbitals, and thereby nickel having the geometry of square planar. All right. So this is about Cn4. So this is nothing but the coordination compounds having coordination number 4, and the kind of geometries they are capable of forming. Now just see one thing. Spin is because of the presence of unpaired electrons. Now when pairing has taken place, is there any unpaired electron? No. So the spin is going to be less or 0. Okay, and will they have any magnetic effect? No, because for magnetism to be shown, there needs to be an unpaired electron. No unpaired electron, thereby this is diamagnetic. Inner orbital complexes are low spin complexes, and they tend to be diamagnetic generally. Whereas when you look at the outer orbital complex, you see there are 2 unpaired electrons. Of course, it is going to have a higher spin, right? And it is paramagnetic. This is something that you need to keep in mind. Now, talking about coordination number 6. We already know that D2sp3 hybridization forms inner orbital complex, and sp3d2 forms outer orbital complex, and both have octahedral geometry. So here geometry is not something that we are worried about. We are worried about what we are supposed to understand is how these complexes are formed. Clearly, pairing will take place for inner orbital complexes. For outer orbital complexes, pairing will not take place. Let's see how this is happening. Okay, so for D2sp3, obviously n minus d, 2 n minus d orbitals are taken, whereas for sp3d2, 2 outer nd orbitals are taken. Now here they have taken the example of cobalt, NH3 taken 6 times 3 plus. Now your very first thought will be, ma'am, NH3 is a weak field ligand, ma'am, it's a weak field ligand. So ma'am, you know what? This is going to form a outer orbital complex. But I want you to understand something. There is an exception. In the presence of cobalt, NH3, okay, NH3, let me not write it like this will cause confusion. NH3 acts as a strong field ligand, okay, for cobalt. It acts as a strong field ligand for cobalt. Thereby it will cause pairing. It will cause lowering of spin, and it will cause or form inner orbital complexes. As you can see, pairing takes place. When pairing takes place, these two orbitals become free for hybrid orbital formation. They participate along with, okay, so 2d orbitals combines with 1s orbitals combines with 3p orbitals, and you get d2sp3 hybridized orbital, okay, d2sp3 hybridized or hybrid orbitals, and they form octahedral complex. And what you need to know is they are low spin complexes because no spin at all, electrons are not there, unpaired electrons, and they are diamagnetic. Whereas for COF6, fluorine is a weak field ligand. Obviously, it will form a outer orbital complex. As you can see over here, it forms outer orbital complex. Pairing does not take place. Thereby, 1s orbital with 1s orbital, 3p orbitals and 2d orbitals combined to give rise to sp3d2 beta. Here there is a mistake, let me correct it. To give rise to sp3d2 hybrid orbitals, sp3d2 hybrid orbitals, sp3d2 hybrid orbitals, sp3d2 hybrid orbitals, and of course it is going to be octahedral. And you see, there are 4 unpaired electrons, so high spin complex, paramagnetic. All right. Now, what is magnetic? What is magnetic property? Now, beta, the magnetic moment of coordination compounds is measured by nu, and this nu, the magnetic moment that we're actually calculating, is a spin only magnetic moment. Okay, spin only magnetic moment. Okay, and its units is Bohr magnetons, BM. Its units is Bohr magnetons, that is BM. Okay, and how will you calculate this? So under root n into n plus 2 Bohr magnetons is the formula for calculating magnetic moment. Where n is equal to number of unpaired electrons. It is nothing but equal to number of unpaired electrons. So this formula is equal to under root n into n plus 2 Bohr magnetons. There are some complications in study of magnetic behavior of coordination compounds of the first transition series. Some complications are there. Okay, but this is the formula, beta. Now, okay, ma'am, VBT has helped us understand the hybridization, the geometry. That's amazing. But there are some limitations. What are the limitations? It does not give quantitative interpretation of magnetic data. Okay, it does not explain the color of the coordination compounds. It does not give the quantitative interpretation of kinetic or thermodynamic stability. It does not demarcate what is a strong field ligand, what is a weak field ligand. And it cannot determine exact predictions regarding the tetrahedral and square planar complexes. It cannot. Okay, ma'am. Then what are we supposed to do? Then comes our crystal field theory. crystal field theory. Now, in this particular theory, beta, in valence bond theory, we are thinking of coordination bond being formed, covalent character is shown, hybridization is seen, hybrid orbitals are formed. All of this is understood in VBT. CFT is a whole new model. It does not talk about the covalent character. In fact, it says that the interaction between the metal and the ligand is electrostatic. Okay, it is an electrostatic model which describes the electronic structure of the metal ion in ionic crystals. It provides an approximate description of electronic energy levels that determine the UV and visible spectra, but not the bonding. Basically, it does not talk about the bonding. It does not. It talks about the interaction between the metal and the ligand. It feels that there is a interaction between the metal and the ligand, and this interaction that they have is purely electrostatic. Right? Now, to understand this better, we need to first understand something that is nothing but the d orbitals. The d orbitals. Okay, in isolated free state, all the d orbitals have the same energy. What are the different d orbitals? dxy, dyz, dzx, dx square minus y square, dz square. All these d orbitals have the same energy, and thereby they are called degenerate orbitals. But this degeneracy is lost when a ligand comes into picture. In the presence of a ligand, these orbitals, they lose their degeneracy and there is a difference in their energies. Okay, so on the basis of d orbitals with coordinate axis, they are again grouped into two sets. We will see how they lose their degeneracy, but they are again further divided into two sets. What are they? One is EG orbitals, that is evenly degenerate orbitals or axial orbitals, because they are present along the axis, which is nothing but the dx square minus y square and dz square. The EG orbitals are known as the evenly degenerate, and they are present along the axis, right? Okay, ma'am. Then we have T2G orbitals. They are triply degenerate. Obviously, 1, 2, 3. 3, no. Here there are 1 and 2 even. Here 1, 2, 3, triple. So they are triply degenerate and they are non-axial because they lie in between the axis. Okay. So this is something that you need to know. This is the prerequisite. This is something you must and should know to understand CFT. Okay. Now let's see what is happening. So there are certain postulates of CFT. What are these postulates? The anionic ligands are treated as point charges. That means the anionic ligand is treated as a point charge. Then what about neutral ligands? So these neutral ligands are treated as dipoles, point dipoles with the negative pole pointed towards the metal. Metal is positively charged, no? Obviously, right? So what are they saying is that these anionic ligands that we have, okay, they are treated as negative point charges. And now what if there are neutral ligands? Then these neutral ligands are treated as point dipoles. They are treated as point dipoles in such a way that the negative pole is pointing towards the metal. Okay, ma'am. So metal is positively charged and the negative pole in case of neutral ligand, or the negative charge, that is negative point charge, is now facing towards the metal. Okay, ma'am. Okay. Ma'am, positive charge, negative charge, there is going to be an electrostatic interaction. Exactly. Yes, to explain that. Now the interaction between metal atom and ligand is purely electrostatic. Obviously, you are putting two separate charges, two different charges, two opposite charges facing towards each other. Obviously, there is going to be an interaction. There is going to be some kind of force coming into picture, which is nothing but your electrostatic force. So it's purely electrostatic. And there is no intermixing of atomic orbitals or no insertion of electron in the metal orbitals. Basically, in valence bond theory, the fact that we saw atomic orbitals are combining, giving rise to hybrid orbitals. To this hybrid orbitals, the ligand is giving or donating its electrons. That That entire, that entire story is not happening here. Here they are playing on a different level. They are like, no, electrostatic, that's it. Forces of interaction are there. And there is no intermixing of orbitals, no insertion of electrons. Okay, fine, this is the second postulate. What's the third postulate? The third postulate is important. Please pay attention. If the field produced by the surrounding ligand is symmetrical, then the d orbital of the metal is degenerate. That means if the field produced by the ligand is symmetrical, then the d orbital continues to be degenerate, beta. But in most of the complexes, the degeneracy is lost. Why? Because the field produced by ligand is not symmetrical. Had it been symmetrical, degeneracy is not lost. Had it been symmetrical, degeneracy is not lost. But that is not what is happening over here. The ligand, the field produced by it is unsymmetrical, as a result of which the degeneracy of the d orbitals is lost. Now, if the degeneracy is lost, what is going to happen in the presence of the ligand field? Loss of degeneracy. These 2 points are very important. Loss of degeneracy leads to splitting of the d orbitals, and in their energy is called the crystal field splitting. Loss of degeneracies causes a splitting of the d orbital. Now we have already marked two categories. One is Eg and the T2g. So it is going to split as Eg and T2g. Okay, that means they are not going to have the same energy anymore. If they are going to split, one is going to see if this is the energy, beta. If they are going to split, if splitting is happening, one is gaining energy and is moving high. The other is losing energy and is coming low. Right? So this is how splitting is taking place. One is gaining energy, one is losing energy. Okay. Okay, ma'am. Now, how is this happening in the case of octahedral complexes and tetrahedral complexes? Let's start with octahedral complexes. How is this splitting taking place? So, 6 ligands are surrounded by the metal atom or ion. Each 2 ligands are directed along the both sides of the coordinate axis. Now, the thing is, if the ligands are directed along both the sides of coordinate axis, what you need to understand is, when ligands are directed along the coordinate axis, the evenly degenerate, that is the Eg and the Eg orbital, sorry. The Eg orbitals, that is the dx square minus y square and dz square will be more affected, no? Because they are placed along the axis, and that is exactly what is going to happen. Since Eg orbitals are more directional towards the ligands, they experience greater repulsion and their energy is higher. That means they gain energy. Whereas the T2g orbitals lie away from the ligands. They lie away from the ligands and hence have lesser repulsion. Basically, so if this is the d orbital, beta. So the Eg orbitals is going to rise up and the T2g is going to lose energy and come down. And that is exactly what you see over here. That is exactly what you see over here. Okay. So this is the free metal ion average energy in spherical crystal field, that is in symmetrical crystal field. But this is not the case. It becomes unsymmetrical. In octahedral crystal field, they split. The Eg orbitals will gain energy and the T2g orbitals lose energy. How much energy do they gain, beta? 3 by 5 delta naught, that is nothing but plus 0.6 and 2 by 5 minus 0.4. 3 by 5 is nothing but plus 0.6, no? And 2 by 5 is nothing but minus 0.4. Ma'am, 2 by 5 is not minus 0.4. Here the plus and minus is showing gain and loss of energy. Eg is gaining energy, that's why plus 0.6. T2g is losing energy, that's why minus 0.4. Okay? Okay? Now, what you need to understand is, this energy difference between the Eg and the T2g orbital after the crystal field splitting is known as crystal field splitting energy. CFSE, abbreviated as CFSE. So the energy difference between the EG and the T2G orbitals after the crystal field splitting is known as crystal field splitting energy, and it depends upon the geometry of the complex, the size of the metal atom, the oxidation state of the metal atom, and the field produced by the ligand. Now, how will you calculate the crystal field splitting energy? -4 into the number of electrons in T2G orbital plus 6 into the number of electrons in EG orbital, where any T2G is nothing but the number of electrons, where any T2G are nothing but the number of electrons present in T2G, and any EG is nothing but the number of electrons present in EG. This is how you calculate the crystal field splitting energy of octahedral complexes. This delta naught is nothing but for octahedral complexes. CFSE, crystal field splitting energy of octahedral complexes. Now, what about tetrahedral complexes? Now, for tetrahedral complexes, what is going to happen is, beta, for tetrahedral complexes, okay, so the same thing is given over here. The energy will increase by 3/5 delta naught and decreases by T2G. Yes. Now, over here, they have given you the list of the strong field ligands and weak field ligands. So you can see over here, CO and CN are strong field ligands, followed by, okay, NH3, EDTA, okay, thiocyanate, and so on and so forth. Okay, so this is the order for crystal fields. This is the order for the strong field and weak field ligands. Okay, and what you can observe from this particular thing is, that this is the trend that it follows. Okay. Now, in D1, D2 and D3 coordination entities, the d electrons occupy the T2G orbital singly according to Hund's rule. Yes, that's true. But for D4 ions, now the fourth electron is in dilemma. Should it enter T2G? Should it enter EG? Now, if there is a strong field ligand, it will enter the T2G orbital. But if it is a weak field ligand, it will enter the EG orbital. Now, here comes a thing that is nothing but pairing energy and crystal field splitting energy, beta. Okay. Now, if the pairing energy is more, that is the energy required to pair the electron is more, then obviously it will not pair, because more the energy, unstable the complex. More is the potential energy, less is the stability. So, more is the pairing energy, more is the energy required to pair. It will like, why should I spend more energy? So, if pairing energy is more than crystal field splitting energy, if pairing energy is more than crystal field splitting energy, then pairing does not take place. Then crystal field splitting energy, that is, it will split and the electron will go to EG orbital. But if crystal field splitting energy is more than pairing energy, that means the energy required to split is more. Instead, I'll pair, no. So, the electron will not split but pair with EG only. This is the one logic you need to keep in mind. Okay. And that is exactly what is given over here. So, if the pairing energy is more, then instead of the electron entering T2G, it will enter EG. But if the crystal field splitting energy is more, then it will enter the T2G orbital and not EG. And this takes place. Strong field ligands have a role in this. Okay. So, in the case of strong field ligands, the pairing energy becomes less. In weak field ligands, the pairing energy becomes more. Or you can say in the case of strong field ligands, the crystal field splitting energy becomes high. And in the presence of weak field ligands, the crystal field splitting energy becomes low. Okay. Now, in tetrahedral complexes, what happens is the reversal takes place. So, in octahedral, you saw that the EG orbitals gained energy and moved up, and T2G orbitals, they lost energy and they went down. In the case of tetrahedral complexes, the T2G energy gains energy and moves up, and the EG orbital loses energy and comes down. And that is what is given over here. That is what is given over here. Right? Right? And I can write I'll write over here. I can write delta T in terms of octahedral crystal field splitting energy. Crystal field splitting energy of tetrahedral complexes is 4 by 9 times of octahedral complexes. This is what you need to keep in mind. Clear, beta? Clear? There is limitations, beta, for CFT also. Yes, there is limitations for CFT as well. What are the limitations of CFT? What are the limitations of CFT? The limitations of CFT is, first things first. If we are considering the ligands to be point negative charges or negative dipoles, then why is it that and look at the strong field ligand over here. Why is it that ligands having electron pairs, lone pairs of electrons are at the lower end, and the ones having are being neutral, does not have negative charge at the higher end? How is that happening? So this is one limitation of CFT. Second thing is, it does not talk about the directional property. Yes, there is directional property. There is directional property. That is how we are able to understand the bonding. We are able to understand the geometry. It does not speak about that. Okay. It does give us an understanding of magnetic nature and color formed in coordination compounds, but does not answer the other aspects. So these are the limitations of CFT. Now talking about metal carbonyls, metal carbonyls. These are some of the homoleptic complexes of metal carbonyls. And one thing that you need to know about metal carbonyls is the carbonyl, CO, carbonyl carbon. It donates electron pair to the metal, but at the same time there is something known as synergic bonding. It also accepts electron pairs, electrons from the d orbital of the metal in its pi star orbital, that is in its anti-bonding orbital. This is known as synergic effect and is known as synergic bonding, which strengthens the bond between the carbonyl and the metal. So this is about bonding in metal carbonyls, and this is what it looks like. So it is donating its electron pair, but is also accepting the electron from the metal d orbital to its structure, to its anti-bonding orbital, and this is known as synergic bonding. This is about metal carbonyls. Alright. So with this, kids, we have come to the end of our session. We have discussed coordination compounds in detail. I hope you are able to understand whatever has been taught. However, if you have any doubts, any queries, any questions, you can always reach out to us in the comments section down there, and we'll cater back to you. Alright. So until we meet next, keep smiling, keep revising, and stay healthy. Bye-bye.